Thanks for joining my session, the last one. So we'll see if it will be one of the best or not. You will decide. My name is Piotr, Głaska. I work for Infoblox, which is a company doing secure DNS solutions. So basically what I do is I do DNS every day, all day. Different kind of stuff regarding DNS. Also having a lot to do with, for example, lookalike domains. That's why you have this picture here with a lookalike. Anybody knows the movie from Netflix series? Who watch it? Vikings? Okay. Basically, I'm a solution architect, but also kind of a threat researcher, a bit as a hobby. But it's just my passion, and I like to do it. My hobbies, all kind of team sports actually. Cybersecurity is a team sport, playing Battlefield in a team, and also dancing urban keys, which is kind of interesting dance, very modern, very technical. So lots of IT guys are liking it. Although usually, if you look at the urban keys teams, they are completely different than this room. So we have lots of girls and much less guys. So I think we should pair, because then it would work much better. Okay. The title of the presentation is around C2, so it's command and control. Just as a short reminder, in a cyber kill chain, command and control phase is almost the last one, right? It's where the bad guys, are connecting from the infected machine to the C2 server, so they can control actions taken on the infected machine, right? So to do that, they need to have some kind of protocol between infected machine and the C2 server. And the protocol needs to be understood on both sides. That's one thing. Second, it should be quite hard to detect by the defenders, right? So usually they tunnel C2 traffic over some kind of protocol which is very popular, and it just makes detection harder, right? So typically they will tunnel C2 traffic over HTTPS, very typical, but also over DNS, because it's also a very popular protocol on the internet. So C2 over DNS, who knows exactly how C2 over DNS works? Please, hands up. Okay. A few hands, so I will also do some introduction. C2, command and control over DNS. How do you tunnel, how do you hide information in a DNS query? So basically, if we have infected host here, and we have some data, I mean, we as a threat actor in this moment, we will send the traffic inside of a DNS query and code it basically as a name for which we are sending the query. So it's a host name and a domain name, right? So the data is encoded usually inside of the host name, sometimes inside of the domain names, subdomain names. Because of that, you need to follow some rules, because it's a DNS protocol. It has some rules, like limit the length of the name, how many characters can be between the dots in the name, what kind of characters can be used. So typically, the characters which are used, it's basically letters, digits, dash, and underscore, and basically host names are case insensitive. RFC is not limiting what you can use actually. RFC is just saying it's highly recommended to use those characters. So typically most advanced threat actors will try to use those, because then they will be not doing any traffic which will be easier detected as an anomaly, right? So data is encoded here as just a fully qualified domain name, and it is sent as a DNS query to local DNS resolver. It is not sent directly to the C2 server, as typically it's happening with C2 over HTTPS, for example, but it's sent just as a normal DNS query to local DNS resolver. And then this DNS resolver is sending this query further on the internet to basically resolve the name into the IP address, right? So it is sending the query to DNS system, and finally it is reaching the server, which is authoritative for a domain name which was used by the attacker. So basically C2 domain name, okay? A big advantage of this technique for the attacker is that actually this host doesn't have to have any kind of internet connectivity because it is not sending anything directly to the internet. It is sending data only to the local DNS resolver, and this DNS resolver has to be able to resolve names on the internet. And it is actually serving as a kind of a proxy mechanism for the malware on the infected host. So wherever you have some kind of, isolated network segments in your networks, make sure that you also look inside the DNS traffic, not only rely on that the firewall will not allow traffic from this host to reach the internet, right? Because they still can use DNS resolvers, okay? So that's the direction to C2 server. Data encoded as a DNS, as a fully qualified domain name, sent as a DNS query to local DNS server, and then further to a DNS system. The other direction, from the C2 server, basically it comes back as a DNS response. Then data is encoded. How it is encoded actually depends on what kind of DNS record was used. Typically, DNS is used to resolve names to IP addresses, so A record or quad A records are used. This is IPv4, this is IPv6. So here we can store 4 bytes of data. Here we can store 16 bytes of data, which is not a big amount of data which you can store. But for C2 traffic, it's usually enough because you need to just send some commands. Sometimes they don't even send like a full line of the command, but just a code or a task number to be executed, which is hard-coded in the malware. So the C2 is just saying execute task number 4, and malware knows that task number 4 is to do this, this, and this, right? So this is enough. You have a lot of possibilities with this. If you need to send more data, then use other records like TXT. Actually, it can be kilobytes of data in this case if you use TCP. And you need to limit this data to different kind of characters, right? But also special characters, anything. So you can use base64 encoding, for example, in that. Sometimes attackers are using different types of records, such as null record, MX. This month, there was a new malware which was using MX records and MX replies to store some data and send to the infected host. Okay, so that's short reminder. Now, how does it look in reality? Here we have a backdoor called Sombrat, which was used, for example, with 5-hand ransomware. And C2 over DNS traffic in reality will look like this one here. So you have basically some data encoded as a host name, and then you have a C2 domain name added, and then C2 server responds with IP address, which is basically not an IP address. This is just 4 bytes of data, which we see as an IP address, right? But you can notice that actually each IP here is completely not related to another, right? Typically, if you ask about host in one domain, you will get IP addresses from the same autonomous system number, or maybe few countries, but it won't be so unrelated like it is here. So if you say anything like that, you should get basically some suspicions. Okay, so back to the story. So as I said, I do DNS every day, and that was the case also on April 6th last year. Basically, I was looking into results of our lookalike domain detections algorithm. And here, I just noticed that for domain observed, which is here Iofogas HU, which is basically an online advertisement portal in Hungary. Very typical target for phishing domains. Algorithm has found different domains, and this one, it's a typical example of a lookalike domain used for phishing purposes. So if you see something like that, you want to basically investigate it, right? So I look at this domain. I saw it was registered by a private person from Russia, which doesn't mean it was a person from Russia, but that was in the registry. But it starts to get more interesting anyway. So what you typically want to do is to do some pivoting. You know, you have a clue, a first domain name. So you might want to pivot to the IP address. Maybe you will be lucky. Maybe it will be not a hosting IP address. Maybe it's a dedicated one. So here we see data from passive DNS that this domain name was resolved recently. In this case, it was April last year, to this IP address, and in the December 2022 to some other IP address. So passive DNS, basically, also short reminder, it's just kind of a sensor, usually put somewhere in the telecom networks, but not only, could be anywhere on the internet. And passive DNS sensor is basically getting a copy of DNS queries sent by this DNS towards internet, right? So if this DNS will receive a query from its clients regarding some domain name, it is sending the query about this domain name towards internet, but also the copy of this outgoing query is sent to the passive DNS sensor. And then when the reply comes back, the reply also is being archived in the passive DNS sensors, right? It's not those queries. So passive DNS sensor does not see who was originally, or the client, who was the originator of the query. So there is privacy here. Only thing seen by passive DNS is that this operator was querying about this domain name, but not specific client. But anyway, later what we can do is we can say, okay, so for this IP, what kind of domain which have given this IP as a reply? So if we have IP, we might want to look what other domains were hosted on the same IP. So this is here. And we see that this IP was given in a response for queries regarding also other localized domain names, like some Vinted in Czech Republic, DPD Czech Republic, the Jofogas case we have seen, and so on, right? So that's cool because from this pivoting we have more domains which are probably phishing domains. But what we see here, it's also quite interesting, right? Because when we go back to this case of a ransomware and Somrat backdoor, you have seen these strange characters in a DNS name. And here we see something similar. And there are 4 domains. One here, which is actually dynamic DNS. Another, which is actually also a lookalike domain for cloudfront.net, because it's written with A. And another one, allowlisted.net, okay? Okay, so let's pivot again. Let's investigate one of these domains. For example, allowlisted.net. What we see here is that in passive DNS archive, for this domain, we see 10,000, almost 10,000 different IP addresses in the response, right? Which is not very usual. Either it is hosting or something which could be interesting. So again, let's look in the passive DNS data, and we see that allowlisted domain was queried for these strange host names, and in a reply, there were different IP addresses given back, and as we see, those IP addresses are not so much related, right? They start with different octets and so on. Actually, if we visualize those IP addresses from the responses, you can see that they are located in a lot of different countries around the world, which is completely unusual. Here on the right side, we have a diagram where we see a red dot in a square, for example, here starting with 96, means that there was an IP reply, DNS reply with IP address starting with the 96 in the first octet, okay? If we have a whole red square, it means that there were so many of these replies that they completely fill the square, right? So we have a pattern of DNS replies generated by those DNS queries, which is kind of useful because later we will notice that several malware families which are using C2 over DNS, they are generating same patterns of replies. So later, if you know the pattern, you can search for other domain names to find out which other domains are used by the same malware. Okay, so who's behind this domain? So we query for name server for allowlisted.net. For example, we ask Google DNS, and we get nothing. No error, so this domain exists, but there is no data. When it can happen? For example, if this name server responsible for this domain is using, for example, geofencing. So it will respond to the queries only for clients from specific country. Might be also some kind of error, but also could be geofencing. So definitely we want to check, basically, if we want to check name server for these domains, we basically should ask name servers responsible for .net. So these are GTLD servers. You ask them, and you see that there are 2 name servers responsible for these domains, hosted on one and the same IP address. By the way, this IP location, according to IP addressing databases, is in Russia, which means nothing. I mean, it could be any other country. It is just what it's stored in the databases. But it doesn't mean it's in Russia. It's just in the Russian IP address space. But anyway, all this information so far are, getting this case more interesting. So what we have right now, we see C2 over DNS traffic in passive DNS sensors. So would be good. We as a vendor, we have a security as a service solution as well. So we might check which of our customers were querying those domain names, right? Because they can be potentially infected. So it could be good that we will inform them, right? So we found 30 customers from different verticals, different countries. There was no relation, like, I don't know, banks only or only telcos or whatever. No, it was spread around different sectors, different countries, so not much of a relation. We send them information about the queries we have seen. So we said to them, like, we see in your network this IP was querying this domain name. Please check what's this IP, what's behind it, who generated this query, why, and so on, because it is suspicious. So they all came back with the information that it was a firewall which originated the query. And actually, always it was firewall of the one vendor. So, potentially, it can happen that the firewall will have some kind of exploit, and it could generate C2 over DNS traffic, because it will be the infected host. Right now, every month, for every week, actually, we hear about some exploits for VPN gateways, routers, and so on. So it happens. But also, there are some other possibilities why a firewall can originate a DNS query for malicious domain name. One of the typical situation is that, for example, defenders are using firewall with some access lists, not for an IP address, but for the domain name. So they are blocking access to a domain name, then firewall periodically will resolve this domain name to the IP address and block communication with this IP. But situation here is a little bit different because in this case, these queries will be periodic. Like, every half an hour, firewall will ask for a malicious domain name. In this case, it was not so periodic, right? Not regular, right? So that's out of the question. But also another possibility, which is kind of interesting, is point 4, that there might be some signatures where the firewall will have an SNI verification, which is server name indicator in TLS encrypted traffic. So how does it work? Basically, if firewall gets a TLS connection, it will look into the server name indicator, will try to resolve the name which is in the SNI to the IP address, and will double check if this IP and the IP the packet is going to is the same. If yes, that's okay. If not, that's not so okay, right? So that's also a possibility. So we have a case like this. We have a firewall, and we asked the customers, okay, do you have SNI verification? They said yes, and indeed it was the SNI verification which generated the traffic. So who actually caused these DNS queries to be sent? What was wrong with the communication? So customers said that basically firewall, for example, if they have some kind of host inside of the network, like this one, they saw traffic coming from the internet to this IP on a TCP 443. And then in SNI, the firewall saw something like that. So one of the DNS queries we have seen in the C2 traffic. So this is strange, because who would do that? I mean, if someone is connecting to this server, he should ask in TLS for SNI also www.server.pl, for example, right? But no, he is asking for some kind of domain, which is probably C2 domain, maybe located somewhere in Russian IP address space, so strange, right? Even more strange was the answer, because after verifying the IP address which was generating this traffic, they came back with responses that it was actually a vulnerability scanner or attack surface management solution from Palo Alto. It's called Expanse. So basically, it's a little bit like Shodan, right? It is basically scanning internet, connecting to different IP addresses, trying to find out what's behind, right? So Expanse was actually connecting to different IP addresses and asking for these different strange names in the server name indicator in TLS connection. So why is that? I mean, why would legitimate solution generate something like that, right? So after some meetings with Palo Alto, with Expanse team, with Unit 42, which I want to thank for cooperation, was very good, we found out that basically Expanse gets some IP to scan randomly. Basically, it is scanning everything on the internet, right? So it gets an IP to be scanned. It's connecting. If it will find on this IP port 443 open, it will connect over TLS, but then it has to find out what kind of host names to use in the SNI, because it doesn't know. It has only IP address, right? So what they do is basically they look in passive DNS data, right? What host names were queried which have given in DNS this IP as a reply. So they will then connect over TLS and connect to this IP, but in CNI, they can ask for www.server.pl, for example, but also, because in passive DNS they see this, they will also ask for this SNI. So then the firewall tries to double-check, do this SNI verification, sends DNS query to local DNS resolver to check what IP address is behind, then the IP comes back, and they check if it's the same IP, right? So that's SNI verification. So that's why actually we have seen those queries on our system. But in passive DNS data, this information was correct. I mean, there was some malware generating this traffic. It was just duplicated by Expanse with combination with firewall, with SNI verification. So it was just an accident that this traffic was duplicated. But at the beginning, there has to be some C2 traffic which was then duplicated, right? So we have a situation like this one, that there was some traffic, C2 over DNS with this IP. Then Expanse gets IP to be scanned. By accident is the same which was seen in the DNS reply for C2 communication. So they connect to this IP, and then in SNI, in TLS, they ask for what they have seen in passive DNS. They send it towards this IP. Firewall is inspecting this traffic, so it is checking this SNI by sending DNS query, getting IP address. So basically here we have a mirroring or duplicating C2 over DNS traffic, which happens in the past. So anytime you have incident like, like this, make sure you will not fully trust data from passive DNS, global passive DNS, because it's very useful traffic, but also can be a lot of trash as well, right? For example, like here, we have a duplication of traffic. But anyway, we start to look for, going back to the original malware, we start to look what we can find more, even though we have no access to the infected host. right? None of our customers were infected. We only seen this duplicated traffic, not the traffic originally generated by the malware. So we start to look at the patterns. We have found more domains, because here you, for example, have 2 domains, and you see the pattern is very, very similar. So if you analyze passive DNS data, you can find more domains used by the same malware. And also, there were several questions, like, what's the malware? After analyzing the queries, we noticed it seems to be similar to a PAPI remote access tool. So PAPI is an open source tool which can be used for testing networks, just like Cobalt Strike, for example. It's just PAPI is much less common because it's quite difficult to configure. It requires more time to set it up. So the question was, what we have seen, was it a PAPI or something else, like a variant? Who is controlling that? One threat actor or maybe more? What they're doing, what kind of communication it is, right? So what we did, we set up our own, deployment of PAPI. We start to mirror the, not mirror, to analyze DNS traffic generated by this PAPI RAT to have a, comparison. We start to, looking also in the open source code of the original PAPI. Also later we found some samples of the malware we have found on VirusTotal, so we also started to look into that and do a lot of statistics. So in total we have analyzed 15 million of DNS queries, and what we have found that the traffic was encrypted, but in the communication and in the encryption, you can sometimes find nonce, which is basically a kind of identifier which you can then use to identify separate sessions. So what we were able to do was to for example, see how many clients a specific C2 domain name has. And when the communication started, when it stopped, when there was another session set up, and so on. So what we have found from that is that each line here represents a single client process. So typically in the same period of time, we have seen 4 to 8 concurrent clients connected to the C2 server. This is specifically to one domain only. And also, what we have seen is there was some reaction, I don't know it, yeah, here it will be better seen, that after we published our research on the internet, on LinkedIn, on GitHub, there was some reaction taken by the threat actors. So for example, they stopped completely using one of the domains. With other domain, for example here, they stopped communication on these ones and hot swapped C2 communication to another one within 48 hours after the research was published. So basically, threat actors are noticing, what is published on the internet, and they might react. Then, as I said, we did comparison between the original PAPI and the decoy doc. So here you have simple statistics like what's the length of the DNS query, what's the length of the DNS response. And this is original PAPI. This is the new variant, because as we see, there are differences here. There are completely new comments with different length, different size of data. So after analyzing also the source code, we noticed that basically comparing to the original PAPI, it was completely rewritten in the new Python versions. They implemented new features which were not available in original PAPI. So for example, there was Bosch transport and clients, which is basically a framework used to work with and deploying new versions of software, for example. So it was quite well organized. There was, for example, possibility of arbitrary Java execution. So most likely the victims So the threat actor know that the victim has some Java virtual machines and they can execute code inside of it, which sometimes makes things a little bit more difficult to detect. And also comparing to PAPI, DecoyDoc had a possibility to hot swap C2 communication from one domain to the other without breaking the communication, basically swap to another domain. So until that moment, in April 2023, we didn't know who is the victim because we just see passive DNS data. I told you that in passive DNS, basically, you don't see who is originally sending the DNS query, so you don't know. We found something, but it was not our clients. So we had to actually wait for others to notice something, right? The victims. And it was around November 2023 that two things happened. First, a Positive Technologies security company from Russia has published an article saying that, and they were referring to our paper, that they found around 20 victims of a threat actor using DecoyDoc. They mention only companies in Russia because they specialize in, they are a Russian company, basically. As you see, these are mostly government institutions, IT companies, space industry. Also, there was one telco. And the same month, actually, before this article, a case of this telco was described on a SOC forum event also in Russia by a company called RT Solar. They also referred to our paper. So basically, we released paper on April 20th, and on April 22nd, they noticed IOC from this paper in the traffic they got from DNS sensor in Rostelecom. And they did very, very deep description of the infection, saying really lots of details. So for example, they didn't mention the customer exactly who was the telco, but it's definitely a big mobile operator in Russia, which was, in this case, infected. The infection was not detected for 9 months. They did not found entry point. So, advanced persistent attack. They found 12 infected Unix, Linux, servers in different network segments. No Windows systems or anything like that, just Unix servers. And they, I don't know, what I understood from the presentation was that they did not initially took actions to shut it down. And what happened was that the threat actor actually noticed they are being observed. And basically, they start data wiping, just to hide all the traces, right? So what they did, actually, they destroyed virtual machines in almost all virtual infrastructure. They blocked access to authentication servers. So for example, when this RT Solar company has, tried to do something on the network, they basically were not able to because they could not get into many devices because authentication was not working. The threat actor deleted also configuration from MPLS switches. So basically, there was no mobile service whatsoever for 24 hours because MPLS was not working. So there was no mobile services, no internet services, basically nothing. Core network was not working. They also wiped totally Huawei storage arrays, which was not difficult because they had admin credentials. So that was another funny detail. Probably they mentioned that it is because I think it was Huawei who was responsible for implementation of the whole solution, and they, the operator itself was not responsible for different things, right? So maybe it was the case. But definitely, wiping of data was not the target here. The target was some kind of data gathering because for 9 months they've had access to corporate email, to GitLab, Confluence, different kind of credentials, other company data, right? So only after they noticed they are being observed, they basically wiped out the data. So then subscribers were without services for a day. And after actually they recovered the services, they had to do them for free because they have no billing system whatsoever, right? So the mobile communication services were running after a day, but running for free. Some client databases were completely lost. And after some time, some unwanted video was streamed on the IPTV channels. Most likely in June. It was not said, but on the screenshot on the presentation, it was this date. Because there was a custom DGoy-doc compilation for ARM Linux, which was installed on a forgotten Synology network storage, just simple box with, but you know, people forget about things like that. Shadow IT is everywhere. So that was used by the as well, and they were able to strike back thanks to that. No idea who was the threat actor actually. There was, you know, still it's not known, but DGoy-doc as such is a kind of a tool based on the PAPI, and it could be used by different threat actors. It's like Cobalt Strike. It's not typical for a single IPT group. Could be used by many groups. So probably we might see more of PAPI-like C2 communication and users in the future. So summary. So sometimes you can find interesting things with basic tools, right? It is just important that you know what you are looking for, that you have some knowledge. Sometimes you can find interesting things. You cannot fully trust global passive DNS data. It is very useful. You can find a lot of things, but you cannot trust them totally. So for example, where we analyze data, we have more trust in DNS traffic we see from our customers, but also we inspect, you know, data from passive DNS sensors from global system. But you have to be careful with that. Sometimes could be misleading, especially after infection. A lot of threat researchers start to, you know, ask about C2 domain name. They try to play with it, so they send some stupid stuff, and then you will see it in passive DNS data, and then it is useless. As you see, sometimes even if you don't have access to the infected host, thanks to the passive DNS data, though, you can analyze and find interesting things. Definitely, incident analysis can take a lot of time, so hopefully, thanks to this presentation, you will save some time in the future when you will have similar case. This is also observation here that sometimes people trust Linux, Unix systems too much. They think they are more secure, they have security by design, so we need to remember that they shouldn't be less protected. And also, you know, we shouldn't forget about this other stuff like NAS storages, CCTV cameras, and things like that, because they often use different Unix variants as well. And as you see, they can be used by the threat actor to easily come back, for example. If you want to read more, there is a white paper, around 40 pages. There is also a GitHub repo where you have a YARA rule to find DGoy-doc, all the IOCs, also PAPI traffic if you want to play with that. If you're afraid to use QR code, you can type that as well, but should be legitimate. I think only this QR code is not valid totally, so after you scan this, you will have to move back in the folder structure, but you will find it easily. Anyway, if you have some other questions, you can send it later, but also right now we have time for the questions if you have any. Just wait for the mic. Just raise the hand if you have a question, and we have a microphone here.
Hey, first of all, thank you for the presentation. Super exciting topic, at least in my opinion. So I would start with a noob question. With regards to, you were saying the subdomains, they seem to be pretty random. Would it help if you would do some sort of natural language processing on them, like character frequency analysis to see whether it's a random string or not? And I'm assuming that usually, you know, if it's super random, that may be somewhat fishy.
Yeah, so detection of C2 traffic over DNS, well, you can do that and you should do that. The problem is that you have also lots of, you know, different API uses different, you know, strange names. So we do analyze like n-gram distribution, for example. So what we do by in detection algorithms, for example, DNS query comes, we take two first characters and we check, are those two characters together typical in natural language? Like, you see AD, that's typical. Many words contain AD next to each other, right? Then, so the scoring of the detection for those two will be low. Then we take another two characters. And then we find like Q and X. That's untypical, so the scoring goes up, right? So finally, you have like, some probability which is higher, but still you can have a lot of false positives because of different systems which could generate something like that, right? So you have to use more attributes to find if it's C2 traffic or not. So for example, you check replies. So what we do in the algorithm, we check autonomous system numbers which are used in the IP addresses to which autonomous system numbers they belong, and we check are those ASNs related or not, right? If we have many ASNs in the IP addresses, that's suspicious, right? So you get more and more attributes, entropy, vowel ratio. For example, also, you might try, for example, calculating entropy not for a single query, but for a bunch of these queries or replies as well. So for example, we check if the reply is TXT, not IP address, but text, right? So we combine several TXT responses, and we calculate entropy for this combined response, right? So basically, with simple malware, which is sending a lot of DNS queries, like 1 per second, it's very easy to detect, right? With this kind of malware, which is sending like maybe 5 queries per day, it's very, very difficult. So everything you do in this detection is about trying to not generate false positives. So you add as many attributes you can to...
Yeah, of course, this is what I meant, like short-circuiting in certain cases, if that's possible, because otherwise you have shown a lot of data in there, which, as you said, takes time. Another question I wanted to ask is with regards to, have you done TLS fingerprinting, like JA3S rules, or fingerprints to detect whether you are talking about, or whether you can identify a certain C2 server?
DNS fingerprinting, you said?
TLS.
TLS.
Yeah.
So we basically we specialize in DNS, right? We don't analyze TLS traffic because we often don't see this traffic. Like in this case, we didn't see TLS traffic at all, right? Because it was not from our customers, and we also don't have a solution which is, the traffic would go through. What we do is a secure DNS resolver, and we see DNS traffic. So we specialize in analyzing that. That's why we don't do TLS traffic, because we don't see TLS traffic. But definitely, if you have access to the traffic generated by the infected host, then yeah. Any other questions? Okay. Thank you very much then. If you have some other questions, shoot me an email. Thank you.